Okay, so welcome. I'm Matthäus. I'm working at the AMD Developer Relations team, which is basically the team which makes games run awesome on AMD. And I'm going to talk a bit about D3D12 and how it's going to affect you in the long run and what's actually going on here. So before I get into D3D12, the question is, why do we actually need new APIs, right? I mean, we have D3D11, we have OpenGL, and what's wrong with them, right? And the problem we see is basically consoles. So you buy a console and the games look awesome, and they look awesome like years after you bought it. And on the PC, at the same time, you're getting like PCs which are like way faster than the consoles, and the games are still not looking like way better. And how is this? And usually what the answers you're getting is like, console developers, they can just max out the hardware. So in ways the desktop developers can't do it, right? So they get low-level access to the hardware. There's basically no operating system between them, or like very limited operating system. There's very limited driver overhead, and they can just drive the hardware to the max. I mean, they can just do everything they want. Also, on current consoles, they have a large number of cores, which are relatively slow, but they can use all the cores to submit work to the GPU to keep it actually busy. Like on a modern desktop PC, it's really, really hard to keep like a GPU like Fury fed with work all the time. On consoles, it's very easy. They can just flush in enough work to keep it busy all the time. Also, a GPU is actually, it's several paths, right? You have like, you can copy while you're actually rendering, and this is not exposed on the PC directly to the developer, so they cannot like, say, oh, I want to copy this texture while my graphics is running. They have no way to express this. The driver has to figure it out. On the consoles, they can do it, so you get like extremely nice streaming in games, where it's like, you never get hiccups, you can just run through a level and everything loads nicely, low memory usage, great. And finally, on consoles, they have custom memory management, which means they can just alias render targets, reuse memory, and do tricks there, which are not possible on desktop machines. And the main reason for this is because desktop APIs actually have been designed until now to be like easy to use. Even for some of you might think like DirectX 11 is not really easy to use. It's actually pretty easy because if used correctly, and even if used incorrectly, you should never be able to crash like the operating system by using DirectX 11. You shouldn't be able to write outside a buffer or something like this. And they're also designed to run on a wide variety of hardware, right? So on the desktop, everyone expects to be able to program all the PCs using the same API. So you have like notebooks, you have like quad crossfire systems, and it's the same API and it has to run across everything, so you have to compromise somewhere, right? And currently the compromise was, okay, we make it easy to program, and then it will run everywhere, and you might not get the max performance, but it will just work. It's easy to use. And the question is, can we make a low-level API which is slightly harder to program, but which will work everywhere still, and get better performance, like more of this low-level access? And yes, we can. So there was a proof of concept, basically, which is the Mental API. And it's a low-level API for the desktop PCs. So it's the same programming model that you have on a console. You can just run it on desktop. And turns out this thing works. Console developers who have experience on consoles can ship games on desktop using a low-level API and actually get good performance across a wide range of hardware, like basically all of the AMD GCN cards, which is still a wide range of hardware, and they got good performance, like in Battlefield 4, for instance. One interesting point here is it's a new API, and typically new APIs, they were like not met with great enthusiasm from developers, but in this case it was easy to pick up, right? If we would have like created Mantle and there was no console API, then nobody would have used it. It would like be, oh my god, why is this so complicated? But because the consoles people are familiar with this concept, they could just use it. There's only one problem with this, and as you might have noticed, I'm from Germany, and in Germany we have a standard for everything, like from the banana to the screw, and there's like, what's the standard low-level API? Mantle is currently on AMD only, and I really like standards. I mean, and everyone likes standards because you can just program one target and it works everywhere. So what's the standard now? And the standard is coming from Microsoft, which is just the standard in DirectX 11 before, and now it's DirectX 12. And as everyone of you knows, Windows is the standard system on desktop operating systems. Like every gamer in the world who is serious about gaming is running Windows right now, and will be running Windows for the next foreseeable future. So what you get with DirectX 12 is basically a low-level API which you can run everywhere, so similar to before, with the new programming model which is more low-level. DirectX 12 is also cross-vendor, so everyone is supporting DirectX 12. not only us, like all major IHVs are supporting DirectX 12 and are behind it. So it's not like some API is being forced on everyone, but everyone has agreed together, okay, this is the API we want to have. We can all write efficient driver for this. So it's really cross-vendor, just as the way it used to be. It's also running on consoles, so which is a good thing if you want to port games between them. So developers can write on consoles and then basically run the same code on the desktop, so you don't even have to like translate it to a different API. And eventually it will also run on mobile. So that's basically DirectX 12 in a nutshell. And I will be talking about a few of the new concepts introduced with DirectX 12. So there's quite a few new concepts in DirectX, like command buffers, resource handling, GPU queues, explicit mGPU, and more. And I will skip two of them. So the first one is resources, which is basically an engine level only problem. So from the side of like someone using an engine, you will never see this. You just hope for the best that the engine developers implement this correctly, and then it will work. So it's not really that interesting. The second one is explicit mGPU, which is like an optimization technique to make sure you can use 2 GPUs to the max by manually basically distributing work between them. Again, this is something the engine developers have to provide to you. There's nothing like you can prepare for this. Things will just be more awesome if it runs correctly. So what I'll be talking about instead is command buffers, which is actually changing the way you have to design games or like the game logic to take best advantage of it eventually. And I'll get into detail why. And the next one is GPU queues and also asynchronous compute, which will require you to change the way some effects are approached to actually get the best possible performance out of it. So let's start with command buffers. For those of you who are familiar with the DirectX 11 model, it's basically you bind something, so you modify the state of the GPU, and then you issue a draw call. That's like how it looks like from the API side. So you bind something, and then you say draw. Bind something and say draw. And the driver is running alongside the application, and then it just like records the stuff, and at some point it submits them to the GPU. So let's look at a very simple DirectX 11 game, which is, so it issues a draw call, and what the driver does, it records this draw call and says, yep, I know what to do. I will do this later when there's enough work, because it doesn't make sense like for every single draw call to go to the GPU and say, look, here's a triangle, draw it, please, and I'll come back to you in 5 minutes. So the game does the next draw call, the driver records it again, the game does the next draw call, the driver records it, and now the driver says, okay, this is enough work, the GPU can be busy now, let's submit this to the GPU. And at this point, the GPU will start rendering on this stuff, basically. So that's like the model you have right now. The problem with this is you can have bad luck. So you issue one more draw call, and the GPU records it, and it doesn't submit because, well, it's only one draw call in the queue, so why should it bother the GPU with it? And then you draw some, then you run some stuff which doesn't draw anything. So you run physics, and you run your AI, and then you end your frame. And that's bad, because you might get a bubble. If the previous submit is already finished, and you haven't submitted anything in between, then the GPU might get idle. Idle GPUs are like engines which are not running at full power. Guys, you don't want this. You could have bought a cheaper GPU if it's running idle. And what happens here is basically at the end of the frame, the driver will also submit it. And if you're lucky, the submit will just take enough time to hit the next one. You will have no bubble. If you have bad luck, you will have a bubble, and you will get less performance than you could have gotten. This is changing with DirectX 12. So the key concept change here is previously the application was doing draw calls, the driver was recording them, and it was doing the submission. So the building of command lists and the submission was the driver duty. And now DirectX 12 exposes this to the user. So the application decides when to build command lists, where to build them, so on which threads to build them, and when to submit them. So it can submit them at the best possible moment, and it can also submit multiple of them at the same time. So how does it look like if the game is properly done for DirectX 12? So we go for the same example as before. So the game is now running on 2 threads, and the 2 threads draw and record something. And as you see, the major difference here is the recording happens on the application side. The driver doesn't even know about the application doing something. It may allocate some memory, but that's about it, basically. You call draw, and it record it in command list inside the game, fully in parallel. So if you have 2 cores, they will run fully parallel. There will be no synchronization here. And you can actually exploit as many cores as you have, basically. So we continue. make the next draw, and now the application says, okay, wait a minute, this is enough, I want to submit this. This is a good moment for me. Then it makes the next draw call and it says again, submit. Because there may be some synchronization in between, but whatever. But the key point is here, the application has this under its own control. It can say submit at the best possible moment for the application, not the moment the driver would decide it. And you can also like submit different queues from different threads and things like this, which went possible before. And now you have more time, basically, to process your physics and your AI if you have an also multi-threaded. But the cool thing is, the GPU is now busy with these 2 submit calls, so all of your graphics card is running while your CPU is busy with the physics and the AI. Unlike before, because unlike before, there might have been a bubble, the GPU was not busy. Now the GPU is busy all the time, and at the end of the frame, nothing is going on anymore. So you can decide when to use it, maximize your GPU usage, and also like combine it with your threading. The question is, why is this so important to be able to record from multiple CPU threads? Well, the reason is because we are getting games which are using more and more threads. For instance, Ashes of Singularity, they're actually simulating like each of the small little tanks and tank turrets and bullets and everything is running, it's simulated. So the engine is already heavily multi-threaded. I mean, like, they can max out, I think, 16 cores machines easily just by running like 1,000 units in parallel. And once you have the engine parallelized in this way, or your game logic is parallelized, I think like games like Cities XL, that's the same, right? You have like lots of independent buildings, you can run them all in parallel. You would also like to have the rendering run in parallel, because that's like the most efficient way. Yeah. So I have a slightly contrived example here, which I will go through for this multi-threaded rendering. So we have this racing game, which conveniently has 6 headlights we want to look at. The moon in the top right is not going to cause a shadow map. And how are we going to do this? Let's assume we have a 6-core CPU like on a console. So how would you do this on a console? Okay, so we have the 6 threads, like 6 hardware threads, and then we run, so like at the beginning of the frame, we issue some draw calls to stream in textures to the GPU, we run some particle simulation maybe on another thread, we run some culling and AI. So the orange boxes are stuff which is graphics related, and the other stuff is game logic, right? Say. And afterwards, we have like 6 shadow maps, so now we can run them all in parallel, which is great. So we traverse the scene maybe once, and then just throw it into 6 different buckets, and then we have like 2 primary and secondary views, like the primary and rear view mirror, while at the same time we're doing physics, and finally we submit some post-processing, and everything is greatly multi-threaded. So this is basically how games are going to look in the future. So you will have to take advantage of this, and you will have to structure your code so you can actually run this stuff in parallel, because otherwise you won't get good performance out of it. So just to conclude on this part, I will come back to the example in a moment. So if you're designing your game logic, you should make sure that you can like also eventually be able to produce draw calls in parallel, or have like individual parts of the engine running in parallel, and then the draw code also run in parallel, like parallel culling or something like this. If you can already integrate this today, you will greatly benefit at the time when D3D12 will hit the shelves, and everyone will have this. So it's like, it's good work to do now. Just think about this, okay, is my update thing parallel? Can I actually execute this in parallel? Is there some serial component in this? Because right now, that's the moment where you can restructure your code without having the API changing beneath you. And then later on, when you get the new API, you're already prepared, basically. The predictable submission is something you will have to keep in mind. Because now you can say when you want to submit stuff to the GPU, you can also do it at the best possible moment. So you may want to like look at your game code and then see if you can do like all of my gameplay and then all of my graphics, and then I do submit, and basically I do all my gameplay again, and avoid stuff like graphics, gameplay, oh, and the user interface. Ha! Before I forget it, then like this late submission stuff or something like this. You don't want this. The good thing is what you get out of this is you either get more objects and more variety if you're like planning for a high-end desktop gaming PC, so you have lots of power to burn, you can just drive more units, or if you're running like on mobile, you can just say, okay, I want to use this to use less CPU because it's more efficient, I'm running more cores for a shorter time, they go into idle, the GPU starts working. So that's like the trade-off you can do here, right? You can optimize for graphics quality or for mobile runtime, basically, just by structuring the CPU code differently. Okay, so let's continue with the example I just had with GPU queues. Okay, so we have now this workload. So we have streaming textures, we have this particle simulation, the 6 shadow maps, and the other stuff. And how do we actually map this on the GPU? That's actually a pretty good question, right? Because we have like 6 or 8 cores or whatever, 12 core machines, and we have one GPU inside, and there's like one PCI Express bus, and how do we get the draw cores actually over to the GPU to execute efficiently? And in DirectX 11, but basically what's happening, we would just do the draw calls one after the other in the correct order, right? So we just stream the textures first, do the particle simulation, then the shadow maps, and then it doesn't even fit on my slide anymore. So that's like the timeline, and let's assume every one of this was like 1 millisecond, and it maybe was 20 milliseconds and was too slow. There's one problem with this approach, as you can imagine here, and this is the following. So this is a GPU, and this is what happens when we're streaming textures. So the red dots are the parts which are getting hot. As you can see, like the big part of silicon you paid like $600 for is not getting hot at this moment, which is kind of sad because you paid for it and it's idle. It's twiddling its thumbs. The next moment, you do your particle simulation, boom, the whole chip is warm, but your memory is cold again. It's another $100 you paid for silicon which is not working. Sad. And you're also not getting the maximum heat out of your GPU. And then you're continuing with shadow maps. And for those of you know, like shadow map rendering is practically a very cheap task on the GPU because it only affects the rasterizer, and the compute units don't have much to do. So if that's the whole chip and it has like 64 compute units, then maybe 2 of them are busy and the front end is busy, but the rest is idle. So that's wasted time again. And this is for all the 6 shadow maps. In many cases, it's like half of the frame, only like a tiny part of the GPU is actually working, which is wasted performance because the rest is idle. It's really idle. I mean, there's nothing going on there. That's like knobs, downclocking, waiting for signals, nothing going on. And then we got to the final parts. So we had the primary view and the rear view mirror. So this is like real graphics. You have pixel shaders, normal graphics. Everything is busy. The whole GPU is lit, and the post-processing as well, which is good. I mean, ideally you want to have this where everything is lit all the time. That's the best case. And that's actually the 3 parts GPU actually consists of. So the one thing is the copy engine, which is like the memory. So you have a way to transfer data to and from the GPU while the GPU is doing other stuff. I mean, as you can imagine, like streaming data in and out, it's not really taxing the GPU very much. It's like PCI Express transfer or something like this. So you can do this while other stuff is running. And that's actually a separate hardware for this. Okay. Guys. Okay. Okay. So let's try like this. Anyone hears me? Okay. So the first thing is the copy engine, which just does copies, so it doesn't do much more than transferring data to and from the GPU. The next thing, which is the compute engine, is basically that's the compute units. So this is stuff which can do computations on the GPU. And it's also used by the graphics. So if you have shaders, they will execute on the compute unit. But you can also just do compute, like without any graphics. Like if you don't rasterize a triangle, but you're just running a compute shader, it will run on the compute engine, and the rest of the GPU may be idle at the moment. And finally, there's a graphics engine, which is basically all of it together. So the graphics engine is like all of the compute units plus all of the graphics-related stuff, like the rasterizer. Yeah. So, and when the graphics engine is running, there's like usually not much else can be running, except you're just using the rasterizer, like for a shadow map. And that's actually represented in D3D12, like by this 3 queue system. So we have like a copy queue, a compute queue, and a graphics queue, and each one is a superset of the other. So everything the copy queue can do, the compute queue can do, and more, and everything the compute queue can do, the graphics queue can do as well. The key point here is you have to assign your work, or you think about how to work matches to the queues, right? So the streaming textures is basically, I'm getting data to and from the GPU. I'm not doing anything else when streaming textures. So I should put this on the compute queue. I shouldn't be streaming textures on the guys, everyone working? Okay, let's try and continue, and if you get diff, then tell me. Okay, so the first thing is streaming textures. You should be on the copy engine. The next thing is like particle simulation or post-processing. This is actually a compute task. You shouldn't be bothering the rasterizer with this because it's only computations which are happening. And like the shadow map and everything else is basically graphics stuff. But not all graphic stuff are made equal, because the shader map, as I just said before, it's a graphic stuff which only runs on the rasterizer. So most of the GPU will be idle. So how do we take advantage of this now? Okay, yeah, we put our maps in the stuff in the graphics queue. Then we run the streaming textures in parallel. Try the next mic. Redundancy for the win. We go on with stream the textures while the shader maps are being rendered. This is basically for free. So I just increased the length of the box because we can stream more textures. It doesn't cost us anything. We can stream the whole time until we need them, basically. And we can also run the particle simulation asynchronously. So the shader map is being rendered, and at the same time, the particle simulation is running. It will take slightly longer, probably because the shader map is also using like 2 compute units or something like this. But we can also just spend more time on it, because the whole time for the shader maps, we could just run the particle simulation and the post-processing. That's power we didn't have to burn before, but we can burn now. One problem here is that the post-process you see, it's actually running during the frame, so it's from the last frame. So you have to prepare yourself for like being able to overlap frames. And how is this going to look like in a more serious game? So if you have a big game, you probably have so many tasks. And if you look at this slide, the key takeaway here is basically half of them can be moved to compute. So like you see the physics, the prepare, the lighting, the shading, so the post-processing, everything. Everything you can move to compute can potentially overlap with the bluish stuff. Like all of the orange and blue stuff can run in parallel. And if you're smart about this, all of the purple stuff can run in parallel as well. So that's basically like the ideal case. So you have all of the GPU always busy all the time, all units of the GPU. And this is what we see on consoles. Console games are taking advantage of this. Like if you talk to your favorite console developer, he will tell you, oh yes, of course, I'm using all the GPU units all the time, as much as I can. On the PC, this wasn't possible. But the important thing is you have to separate graphics from compute stuff. So you cannot just take your compute shader and then hope for the best on the graphics queue. You really like take most advantage of this. You want to have compute tasks in compute shaders, graphic tasks in graphics, like normal shaders and everything, and separate them out. So if you have your post-processing, which draws like a full-screen triangle and everything, you really want to move this into a compute shader eventually. So you can run it in parallel, you can schedule it more freely and everything. So this is a new addition from DirectX 12. It gives you this GPU queues to allow the full GPU to be utilized. And this async shaders, which can run alongside the graphics code. The cool thing about this is you get better streaming, higher quality, and faster frame rate, and you can pick all 3 and keep them. It's not like this, oh, I can better streaming, higher quality, but it will run 1 frame per second in SIGGRAPH paper stuff. We really get all the advantages, and there's basically no loss here, because the units are in hardware, they are available, they are just idle. Now they are not idle. So that's like the only difference to what we had before. Important thing here is you have to move stuff to compute. Okay, so let me conclude here. What's the key takeaway? So what's DirectX 12 changing for people like doing graphics or engine users? Like multi-threading is becoming extremely important. I mean, you've heard the story like many, many years. Like we have more and more CPUs, we need to multi-thread, blah, 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 blah. I've heard it myself like 10 GDCs at least. Now it's really important. Trust me, this time we mean it seriously. If you don't multi-thread it, it will not run fast. And we have proved this time that we are right, because on consoles it is multi-threaded, so it's not like talking me out of my... The next thing is you have to prepare for frame overlapping. If you really want to take best advantage of all units on the GPU, you will have to be able to like schedule the streaming from the next frame with the rendering of the current frame. So you have to think about how does your graphics code look like, when does stuff happen. So the one thing is, when does your gameplay run, when does your graphics code run? This is like the first thing you have to keep in mind, and you have to be very aware of what's going on. You can no longer just issue draw codes at random during the frame. You really have to know what you're doing, and you also have to know like how much of this frame can I do during the next frame, because it's no longer important in this frame. Like I can run the post-processing from the last frame when the new frame is starting, as long as I have the buffer available, right? So you have to start thinking in this mindset, which is very different from before, because previously you would say, okay, I have one frame and this is like my basic atomic unit. And now it's like, okay, I have multiple frames and I have overlapping stuff. And it's like similar like on the CPU, you have multi-threading. Now we have on the GPU, you also have like multitasking, basically. Finally, the important part for every one of you writing effects is your super fancy Defo field Uber shader should be probably a compute shader now. Because people will want to exploit this. On consoles anyway, on desktop as well. And they cannot exploit it if your shader is not a compute shader and it's only doing compute. Sure, they can still run it in some kind of way, asynchronously and overlap stuff, but they lose a lot of freedom. They get like the best possible performance. You have to have it in compute so they can schedule it freely, put it on the compute queue, run it whenever they want it, and get the GPU busy at the moment in time where it suits them best, which is very important for you because lots of people are used to still like implementing depth of field, ambient occlusion, everything in pixel shaders. Now is the time to stop doing this. Start using compute. The console guys are doing this as well. We have proof. Ask me if you need proof. It really works. And at the end, you will get the profit. You just implement this stuff, and you will see, going forward, your game will run better and run faster on all hardware which is out there, and you would probably even use less power on mobile. So that's so much for me from today. You can find me on Twitter if you want, and I think we'll also be uploading the slides shortly afterwards.